Welcome back. We're in section 4.8. We're going to talk about three big ideas: the kernel, range, and the rank nullity theorem. Kernel and range are attributes of a linear transformation. So these are going to turn out to be specific vector spaces. So remembering what a vector space is, these are specific vector spaces related to a particular linear transformation. And then the rank nullity theorem is a major theorem in linear algebra that relates the dimensions of these two things. So we'll see that these are both vector spaces, and this theorem relates the dimensions of those two vector spaces. Okay, I think the best way to approach this section is going to be through starting with an example. And for this example, we're going to start with an arbitrary linear transformation. So consider the linear transformation T, and I haven't told you the domain or the codomain yet, but T is going to be defined by you give me a vector x, and the transformation T says we're going to take the matrix A and multiply it by x. So the linear transformation T is defined by this matrix here. Now, the question is, what is the domain of T? What sort of vectors do we multiply by A? Well, it better be a vector in R4, because that's A is a 3 by 4 matrix, so we need to multiply it by 4 by 1 vectors. So T is a transformation that, as its domain, takes vectors from R4. And what is the result? What do we get out after we take a 4 by 1 vector and multiply A by that vector? What is the resulting size? What's the size of the resulting vector? Well, this is a 3 by 4 being multiplied by a 4 by 1. So the resulting vector will be a 3 by 1. So it looks like you start off with vectors in R4, but the transformation takes them into vectors in R3. And that's not uncommon. That's totally legal that a transformation can move between vector spaces like that. And it's all done with this matrix here, just multiplying vectors by this matrix. Okay, I just want to take note of I really want to keep track of what's going on here. So I want to remember that in this transformation T, we start with our domain is R4. That's the vectors that we are putting into the transformation. And then what we call the codomain is R3. This is the vector space that the transformation is taking these vectors into. I'm now going to define a new vector space called the kernel. And this is going to be the set of all vectors in R4 that when you put them through this transformation, they all get sent to the 0 vector. So this is a very important set in the domain. All of these guys through the transformation are going to go to the 0 vector in the codomain. So this is true for any linear transformation. It doesn't have to be this particular one. The kernel is going to be defined as all the vectors in the domain that are mapped to the 0 vector through the transformation. And this is sometimes written KER parentheses T, so the kernel of your transformation. And our first real job in this example is to find the kernel of this transformation, which is the transformation is represented by this matrix. We are going to find all the vectors sent to the 0 vector when they get multiplied by A. How would you do this? How will we find these vectors? Well, let's start by writing algebraically what this says. A times some vector x is going to equal the 0 vector. Okay, so here's A, and then I'm going to take that and multiply it by some vector x, and I need 4 elements. It's a vector in R4. And when I do this multiplication, I'll get a vector in R3, because there's 3 rows to A, and I should end with this. Okay, this is not too bad. We know how to solve equations like this. We've been doing this from early on. We all know one vector that would work. If this was 0, 0, 0, 0, that definitely gets mapped to this one. But the question is, are there others that would get mapped to this? And in this case there are, and we want to find them and be able to describe them. And a good way to solve this system is to put it in a matrix, an augmented matrix, put it through reduced row echelon form, and then read off the solutions from that form. So based on the reduced row echelon form of this matrix, it looks like we're going to have a whole bunch of vectors that will get mapped to 0, 0, 0. So we're just going to take this matrix and interpret it back into the solutions. And we'll have to let x3 equal r and x4 equals s. And then we could say, just based on this row right here, that x2 equals the negative of x3. So x2 equals negative r. x2 equals negative r. And the top row tells us that x1 minus 2x3 plus x4 equals 0. And x3 is just r. And x4 is just s. So we can say x1 equals 2r minus s. And we have a description of all the vectors that are in the kernel. So the kernel of T is the set of all vectors that look like 2r minus s. Let's see, x2 is negative r, x3 is r, and x4 is s. We usually don't write it like this though. We would write it like r times 2, negative 1, 1, 0, plus s, negative 1, 0, 0, 1. And so we can see that the kernel of T is, these two vectors here form a basis for this vector space. So the kernel of T is just any linear combination of these two vectors here. Okay, I really want to convince myself that I've found the right set. So I'm going to say, let's pick, let's let r equal 1, s equals 1. Then if r is 1 and s is 1, the vector that we get out is 2 minus 1 is 1, negative 1 plus 0 is negative 1, 1, 1. This vector here should be in the kernel. Is it true that this vector, when you take a times this vector, you get the 0 vector? Let's see. 1 minus 2 is negative 1, plus 1 is 0. Yes. Negative 1 plus 1 is 0. Yes. 1 times 1 is 1, minus 2 is negative 1, plus 1 is 0. Yes, absolutely. This vector here is in the kernel. If you were to replace this x1, x2, x3, x4 with 1, negative 1, 1, 1, then this statement would be true. That vector gets sent to 0 through this transformation. And you could let r and s be any numbers, and you would find a bazillion, infinite number of vectors that are in the kernel. So this is a really specific example of a vector that's in the kernel, and we'll say along with a bazillion other vectors, and when I say bazillion, I mean an infinite number. Before we move on, there's one thing that I want to point out. The kernel of a transformation, a linear transformation, is a vector space. It's not just a set of vectors, it's an actual vector space. It follows all the rules of a vector space. And so we can talk about the dimension of a kernel, and the dimension of this kernel in this example is 2, because there were 2 elements in the basis. These 2 vectors will generate the whole kernel. Okay, so I want to continue with this example, and we're still talking about the transformation T, which is represented by this matrix that's going to get multiplied by vectors and send them to new vectors. We've talked about the kernel. There's one more important vector space related to this transformation that we want to talk about, and that's the range of T. So the range of a transformation is all the vectors in the codomain, so that's where everything's getting sent to, that are images through the transformation T of the domain. Okay, so this one we want to really think through and make sure we're understanding what it's saying. And at this point I think that a picture of the vector spaces and the domain and the codomain is a good idea. So for just a minute we're going to step away from this specific example and speak more generally. You have some linear transformation T that sends vectors from some vector space U to another vector space V. And we've just seen that the kernel is a very special subspace in U where all of these guys get mapped through T just to the vector 0. Everything in the kernel gets sucked in through the transformation and just collapses into the vector 0. So the kernel is all the vectors in U that get mapped to the 0 vector. Well, the range of a transformation is slightly different. It is taking all of the vectors in your domain. And where do they get mapped to when they get mapped through the transformation T? Do they take up all of the codomain? Maybe, sometimes, but it's often the case that they don't. All of these vectors might get mapped just to a smaller set in the codomain of V, and this smaller set is the range of T. So think for a minute of our example up here. This is taking things from R4, vectors from R4 to R3. Now, when we take these vectors from R4, are they going to encompass all of R3? It turns out in this case they're not. They're just going to be sent to a small subspace of R3, and we want to be able to describe that subspace. So the range of a transformation is the subspace of all vectors in the codomain V that are images of vectors in U as they go through the transformation of T. And just like the kernel is a vector space, the range will be a vector space also. So with all of this background information here, our task now is to find the range of T, find that vector space. So this is a very important job. When we say find the range of T, we're essentially asking, you take any vector in R4 and multiply it by this matrix A. What are all the possibilities for what you could get out of that multiplication? And when you think of this multiplication being done, you know that it looks something like this. Well, another way of writing all of this is just this. And so it is true that this range of T is the span of these 4 vectors. The range of T is the span of the columns of A. So to find the range, we just have to look at and see what those columns are spanning. But we can already see that there's some total duplicates. Like, we don't need both of these columns because they're identical. And actually this column right here I can tell is a combination of these 2 columns, a linear combination of these 2 columns. So to determine which of these columns are linearly independent, or how many linearly independent columns we have, we're going to write these column vectors as rows of a matrix and compute the reduced row echelon form of the matrix, and that will tell us how many of these are linearly independent. So we're going to write the columns of A as rows in a matrix, find the reduced row echelon form, and that will then give us a basis for the range of T, which is what we want. Essentially, we want to shed anything extra. This one I can tell right, just by looking at it what the extra things are, but typically in a matrix we can't tell which columns are, the extra columns. And we definitely want the range of these columns, or the span of these columns, I mean, but we just have too many of them in this case. There's too many, not all of them are necessary, and so we need to get rid of the ones that are not necessary. And once I go through reduced row echelon form, this is what I get out. So these are the only 2 necessary vectors. The range of T is any linear combination of 1, 0, 1 and 0, 1, 0. So this particular transformation is going to take all of R4 and it's going to map it to a smaller set in R3. And this set in R3, the range, all of the vectors have to look like they came from these 2 through a linear combination. Okay, one important note, the dimension of the kernel of our transformation, that was 2 because there were 2 vectors in the basis for the kernel. So the dimension of the kernel, which is 2, plus the dimension of the range, and the range is of dimension 2. There's 2 vectors in that basis. Let's see, 2 plus 2 equals 4. That was another important number in this example. 4 was also the dimension of the domain. So 4 is the dimension of the domain of the transformation. Where we started in this 4-dimensional vector space. This is a fact that will always be true, that the dimension of the kernel plus the dimension of the range will always equal the dimension of the domain of any linear transformation. Okay, at this point I have to reveal that the kernel also goes by another name. like sounds like a soap opera, but the kernel is also called the null space. You'll see this sometimes, and kernel and null space mean the same thing. And the dimension of the null space is sometimes called the nullity of T. So nullity of T. And one thing we know about matrices from a few sections ago is the rank of this matrix A is the same thing as the dimension of the range. You know, how we found the dimension of the range of the transformation is essentially we were looking for the rank of this matrix. And so another way to describe the dimension of the range is the rank of T. So I'm saying that the nullity of T is the same as the dimension of the kernel. That's just a name change. And the dimension of the range, because of how we found it, that is the rank of the transformation T. And when you add these together, this equals the dimension of the domain of T. This is a famous theorem called the rank nullity theorem, that the rank of a transformation plus the nullity of the transformation will always equal the dimension of the domain, the vector space that you start with. So we saw that these numbers just happened to work out in this one example, but it didn't just happen to work out. This is a general principle of linear transformations, that you take all of the vectors that get mapped to the zero vector through the transformation. What's the dimension of that vector space? You add it to the range, the dimension of the range of that transformation. You know, how big is the set of where things are getting mapped to? And when you add these two things together, you will always get the dimension of the domain of this vector space that you started with. So this is an important theorem that we want to hold on to. We went through this example just to kind of show how it works out, but it works for any linear transformation. So for any linear transformation, this theorem will be true. So before we leave, there's one special case that we need to think about with the kernel. It is possible that the only vector that gets mapped to the zero vector is itself the zero vector, that the kernel is very, very small, that there's nothing else that gets mapped to zero except the zero vector. That's definitely true. That happens all the time. So sometimes the only thing that's in the kernel is the zero vector. We do have to ask ourselves, what is the dimension of this? And the dimension of the set that is just the zero vector is 0. And you might think, well, there's one thing in there. Why can't the dimension be 1? There is that one thing in there. Remember that the dimension is counting the number of vectors in a basis of vector space, and the zero vector space is kind of a unique one. It has no basis because there are no linearly independent vectors that will construct it. The zero vector technically by definition is not a linearly independent vector. So the dimension of the zero, the vector space only consisting of the zero vector is 0. So that's important to know when we're counting dimensions, because sometimes we'll run into things where the nullity or the kernel is just that zero vector, and we have to know that the dimension of that vector space is in fact 0.